Okay, hello everyone. Um, it is a Monday night right now, and what I'm going to try and do in this video is teach you all the stuff that we're going to need for the test, specifically for determinants on Wednesday, for all of us, and really anyone can learn how to do this. It's just for those people specifically, but don't worry, you can watch the video and try and learn how to do this because really all you need to know for um how to do these is just basic arithmetic really. It's just really math that you kind of learned in sixth grade. It's just a bunch of it. It's a lot. But other than that, it's really not that complicated. But anywho, I'm gonna get right into it. With one of the four things that we're going to need for the test, which is upper and triangular or upper and lower triangular determinant method or whatever it's called. But yeah, I'm going to give you an example, and I'm going to try and explain it as best as I can. All right, I'll be back with the example. All right, so this is the example. This is the matrix I'm going to use, which is a 3 by 3. Um, and by the way, for triangular matrix method, you're always going to get a square matrix, but I'm pretty sure that's the case for any determinant. I'm pretty sure you need a square matrix for every to find a determinant. Like you can't have one with that. But anyway, um, I'm going to work out specifically um, the lower triangular method for this one, and then I'll do this same thing again. Oh well, no, yeah, I'll probably just do this same matrix again, but just upper. And I'm gonna do lower first because it's easier. And I'm gonna work it all out, and then I'm going to explain. Sorry, long day. But yeah, I'm going to explain what I kind of did for my steps and all that good stuff. So yeah, I'll be right back. All right, cool. So this one was actually really easy. I'll actually probably just do another example because this one was way too easy and we're not going to get something this easy on the test. But anyways, um, but I'm just going to try and walk you through the basic steps of what you want to just do for the triangle method. And what we want to do for the triangle method is essentially for every single leading diagonal, right? We want zeros below that. So in the top left, right? In the top left diagonal, right? Which is this, which is 2. We want zeros below all of that. And then just keep going down. So boop, boop, right? So in the next diagonal from it, from this 2, we have the 0, right? So we want a 0 below this. Well, really, I guess it'd be better to start here because this is our actual matrix. But it's the same idea. We want zeros below this 2, right? And then going down the diagonal, we have this -3. And so we want a 0 here. And once we go to the next number in the diagonal, which is -2, we have no more room. So we know that it stops there and we do not need any more zeros. Specifically for the lower triangular method, which will always have a triangle looking pattern in the bottom left. And then the upper triangle method will have a triangle looking pattern for zeros in the top left. So it would be probably I don't know, boop boop, or yeah, something like that. But in this case, I did the lower triangular method, which is going to have a pattern of zeros that looks like a triangle. And this is why it's called triangle method, because the zeros that you have, right, it's going to look like a triangle, like the kind of way it shows itself, I suppose, right? And basically, kind of like by coincidence, I had this 0. I also got this 0 here. Well, no, yeah, it's basically a coincidence. Just a nice little quinky dink. But any way you work this problem, though, you would probably have to get a 0 in this leading diagonal. Because the determinant for the triangle method is going to be all of the numbers in the diagonal multiplied together, which is why it's 2 times 0 times -18, which is anything multiplied by 0 is always going to be 0. So that's the determinant for this. And yeah, so not too bad. And yeah, so nothing too crazy there. I hope you understood that. And the operations that you can do for the triangle matrix are honestly like the regular matrix operations that you're probably used to. And for those who are uninitiated, the notation I have for here, right, is so R is just basically row, and then whatever the subscript is indicates the actual numbered row. So R1 is row 1, right, which is these 3 numbers. And then row 2 would be this row with these 3 numbers, and then row 3 would be this row with these 3 numbers. And so basically what I'm doing here is I'm just trying to add together rows and scalars of these rows. And what a scalar is just, I'm like either like sizing it up or sizing it down depending on what numbers I need in order to make these numbers right below the leading diagonal zeros to make that triangle. And so yeah, that's what I kind of just did here, right? Really simple. And it just kind of worked out to be super easy. It's usually not going to be this easy. I'm not even gonna lie. For the most part, you're probably gonna have a lot of trouble with these triangular, using the triangle method. I'm not gonna lie, it's not exactly an awesome method to use. Sometimes it just works out, but honestly, I don't really like it because it's like, it can get kind of annoying sometimes. But anyways, I'm gonna move on to, should I do another example? I'll come back to this in case I have more time, but I probably will. Anyways, I'm going to be moving on to the mechanical method, or really the shoelace method for finding the determinant. And specifically, just kind of describing what the shoelace method does is that it gives you the area, or not the area, it just gives you the determinant of, well, it does give you the area, but that's not exactly important for the video today. It just gives you the determinant of kind of like a polygon, basically. And for specifically the test, our teacher is going to give us points, right? So what I mean by points is like, coordinate points on a XY axis plane, which is going to be like, for example, like the origin 0, 0, which is, really basic, or something like 5, 1, X being the 5 and Y being the 1, and other points that he just feels like giving us. I mean, it really doesn't matter too much, but I'll be doing an example of that shoelace method here, and he also doesn't really care if we give him an actual explanation of what the shoelace method is giving us. It does give us the area of a polygon, so yeah, pretty cool, I guess. I mean, nothing too crazy there. Well, I mean, to like, I don't know, like a random outsider, maybe it could be pretty crazy, but honestly, it's like not that crazy for Math Cluster. Man, I ran and my hair is weird, but whatever. I'm taking a shower right after this. Okay, I should have took one already, but I was just tired, to be honest. I still am. But anyways, moving on. I will be, well, actually, yeah, I'll just stop the video and write out the example problem. And yeah, so I'll be right back. Alright, cool. So honestly, I'm just gonna work this out right in front of you, just to like kind of show you what I'm doing here. So for this example, right, I guess we're given 5 points, right? A, B, C, D, E, right? And these are kind of the specific actual coordinates for each point, right? So what I'm doing here, right, is I'm quite literally, for the shoelace method, I'm just putting every single coordinate, and I'm kind of just flipping it right here, right? So like 0, 2, right? 0, 2, 2, 0, 1, negative 1, 0, 0, and negative 2, 0. Boom, boom, right? And then what you want to make sure that you do is you always want to make sure that you loop back around to the 0, 2, right? So you start and end, kind of like a nice whole Om kind of Buddha meditation shit. I don't know, man, but yeah, pretty cool, right? Well, not cool yet. We haven't solved it, but yeah. So I'm just gonna work this out right in front of you because honestly, it's not too bad. So what we're gonna do here, right, is just do major minus minor, right? And I'll show you what the major is. So the major, right, for those who are uninitiated, the major kind of part of this is it's always going to be from the top left to the bottom right. So boom, 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 right? So all of these that I kind of attached together, right, with this imaginary shoelace or whatever you want to do it, and chains. I don't know if you're into that stuff, but hey, it's not my problem. So yeah, with these imaginary lines or shoelaces, whatever it is, right, we're going to multiply all of these together and add them up. So it's quite literally going to be 0 times 0, which is 0, plus 2 times negative 1, which is negative 2, plus 1 times 0, which is 0. And I'm just putting most of these in parentheses because I just feel like it, to be honest. And, alright, my bad, I'm back. So, right, 0 times 0, 2 times negative 1, which is negative 2, and then...
You got something out here, baby. It's, Grandma wanted to know if you wanted it.
I'll look at it later.
It's college stuff.
Okay.
What happened to this thing?
It do be like that. Anyway, so yeah, 0 times 0, blah, 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 right? And then 0 times 0, and then negative 2 times 2, right? Which is just negative 4. And this is the major, right? And then the minor, which all of this... So let me just add up all of these together, right? So this is basically just going to be... Wait. Did I miss one? 1, 2, 3... Oh. Well, yeah, that's 0, that's 0, so... I mean, I should have added one more 0 here, but it doesn't matter, because 0 doesn't do anything. So, all of this... All of these, right, is going to be just negative 6. But, so yeah. Now, I should have had the one more 0 here just to kind of indicate that I multiply all these together, but I'm sure you can see that either way it's still gonna add up to negative 6 at the end for all of these added up together, right? And then, so this is the MA, or the major. So this is the major number, right? And then the minor number, well, I'm actually not 18 yet, so I can still be like, I don't know, I mean, it's gonna be crazy because like, when I'm 18, my girlfriend's gonna be 17, and that's not cool. It's just, I think I'm cooked, chat. But anyways, so the minors, right, is gonna be these, right? Multiply together these, and these. So it's just from the bottom left to the top right, right? So it's just like kind of flipping that. And so the minor, right, is 2 times 2. And I'm not gonna have the parentheses for this one because I don't feel like it. So 2 times 2 is 4, plus 0 times 1, which is 0, plus negative 1 times 0, which is 0, plus 0 times negative 2, which is 0, plus 0 times 0, which is also 0. So quite literally. Yeah, because boom, 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 boom. Yeah, literally, it's just 0 or not 0, 4. And this is the MI, or the minor number. And obviously, since this is the major, right? The major is dominant. He is in the minor is very submissive. Wait, I mean, in this case, if we were to like say like I'm the minor, because I'm submissive, no pause. That's just factual. Sorry that I'm going on a rant here, but it's I don't know. It's kind of funny, I guess. I don't know. But yeah, major minus minor. So, um, I don't know. I mean that's just kind of. Well, actually, because for the shoelace method, um, it's always going to be 1/2 absolute value, major minus minor, and so it's basically just going to be equal to 1/2 -6 minus 4, which is -10, which is going to be 1/2 of 10, which is 5. And that's it. You can't really see that very well, but there you go. So yeah, that's it. That's the determinant. And we're done. So that's it. That's all you got to do for shoelace method. And so yeah. Yeah. Oh, right. I should probably pause the video. That took me too long to write it out, but whatever. So, let me explain all of this. So, this is specifically adjoint matrix and finding the inverse through that. So, let's just kind of look at where to start with something like this. So we're given a matrix, and in this scenario, it's matrix A, which is equal to this matrix here: 2, 0, 3, -1, 4, -2, and 1, 1, -3, 5. Right? So all we're going to do here is we're going to find the cofactors of every single element, or really what the element is just every single number in the matrix that we're given, which is right here, right? And to find the cofactors of every single number, all we're going to do is essentially for the first element in the first row, right? So row 1, which is, and this is the notation, by the way. This is cofactor row 1, column 1. So row 1, column 1, boom, boom, is 2, right? So the cofactor of 2 is simply going to be, so you cross out row 1, right? Because it's row 1, column 1. So cross out this row 1. So just kind of leave that row blank and then leave this column blank. And then you get these numbers, right? What the hell? Yerm. I think I wrote it wrong. Oh, I did. My bad. Because I'm just doing this based off of my example, and I just wanted to write it a little fast, so that's my bad. 4, -2, -3, and then 5. Perhaps that's something I should kind of keep in mind of, proof checking or whatever it's called. And then wait, see what? -1, 2, 1, 5. -1, 4. Yeah, I think all these are right. And so yeah. So you cross out this row 1, right? You leave it blank, and then leave this blank, and then you get this kind of minor matrix, right? Which is just to find the determinant is, and that's what we're doing to find the cofactors. By the way, we're finding the determinant of these minor matrices. And if you'll remember from earlier on in our linear algebra class, to find the determinant of one of these 2x2 matrices is to multiply the major right? Which, as I kind of explained before, was the top left and the bottom right. So you multiply these together, right? Which is 20, right? 4 times 5 is 20. And then you subtract that from the minor, right? Which is going to be negative 3 times negative 2, which is 6. So 20 minus 6 is 14. And then you kind of just do that with the rest of these. But one very crucial element, that you want to be very aware of. You know what? I'm gonna go get some water. Whoa. One element you need to be very, very aware of when you're doing the cofactors for all of these numbers is that if these kind of numbers right here, right, for the row and column, when you add them up, if they're even, you multiply this regularly, right? But if they're odd, like 1 plus 2 is 3, right? Right, for the row and column. If it's odd, you multiply the whole thing by negative 1. And so, right, so 1 plus 3 is even, so no negative 1 we multiply here, right? But 2 plus 1 is 3, right? So I multiply this thing by negative 1. And then you just do that for every kind of odd thing you have. But every even even kind of number you get when you add these together, 3 plus 3 is 6, so you don't do anything to that, right? And then, yeah, so once you get all of those cofactors, you want to put them into a matrix, right? And that's what we did. Oh, that's what I did, I guess, but whatever. So 14, right? 14 here, boom, 3, negative 1, and then just keeps going, and then, yeah, and this is the cofactor matrix. And, so yeah. And now that I have the cofactor matrix, I can find the determinant of A, which is a part of the equation that I need to actually find the inverse of this matrix, which is what we're actually trying to solve for, by the way. We're solving for the inverse matrix through the adjoint matrix. And first, finding the determinant of this is quite easy. All you have to do is like kind of connect the cofactor elements of like one row or column with the original numbers in the original matrix, and then multiply them together, and then add all of those in the row that correspond with each other together. And I'll show you what that kind of means. So take, for example, row 1, which is the specific row or column that I wanted to use to find the determinant. And specifically, I used row 1, right? So it's going to be 14, right? Which corresponds with row 1, column 1, which is 2, right? So 14 times 2 is 28. And then, since I'm using row 1, I'm going to go with, obviously, 3 right here, which corresponds with 0. 3 times 0, right, is 0. And then I add this next one in the first row, which is negative 1 times 3, which is negative 3. And so 28 minus 3 is 25, and that's the determinant. And I hope you got that, because it's really no super easier way to explain that. It's just kind of how you do it. And to find the determinant, I could use row 2, row 3, and there's the corresponding, numbers for each cofactor. But other than that, yeah. And you don't have to use rows. You can also use columns if you wanted to. Now, what I recommend is to simply use the easiest, or not the easiest, but the smallest numbers possible to make the calculations trivial, super easy for you. I just felt like using row 1 as a good example. But yeah, so I have the determinant of the original matrix, right, which is 25. And that's going to be a part of our inverse formula here, right? So to find the adjoint matrix, right, all we're going to do for the adjoint matrix to actually just get it, right, is to take this cofactor matrix we made, right, and to transpose it. And to transpose a matrix is it's really easy. All you have to do is take the row, all of the rows, and then flip it into the column that it corresponds with, right? And what I mean by that is row 1, right, which is 14, 3, and negative 1. So row 1 turns into column 1, right? So row 1 right here, right? So 14, 3, negative 1 flips row 1 into column 1 here, right? So 14, 3, negative 1 in row 1, and then it turns into column 1. And then same with the next row, which is row 2, negative 7 and 6, 6, 7, flips into column 2. And then same with row 3, negative 12, 1, and 8 flips into column 3. And that's how you transpose a matrix. And the transpose of the cofactor matrix is the adjoint matrix. And so this is our adjoint matrix, right? And then all we need to do, right, for the inverse matrix is just 1 divided by the determinant of our original matrix, right, which is 25. So 1 over 25, right, multiplied by the adjoint matrix, which is just this whole thing. And that's what I did here. And so this 1 over 25 multiplied by the adjoint matrix is our inverse matrix. And that is it. So, yeah. I hope you got that, because I low-key can't explain that again, because that's that. So yeah, I'm gonna move on to Kramer's rule, and yeah. So I'll be back with the example and the explanation. All right, so Kramer's rule in comparison to like everything else, it's pretty easy. But you know, if it's not easy to you, I'm here to explain. So we're for Kramer's rule specifically, we're gonna be given a set of a systems of equations, right? And it can be in the format of x, y, z, or really any 3 variables. I just use x, y, z because I felt like it in this example. It could be x1, x2, x3, or the normal x, y, z, but it doesn't really matter too much as long as you know how to like easily convert it into a matrix, because that's what we usually do, right? So for the A matrix, we're going to take everything on the left side, right? So x, there's 1x here, there's 3y, and there's 1z. So 1x, 3y, 1z. And then for the second equation, it's going to be 2x, 5y, and 1z. And then for the third, it's going to be 1x, 2y, 3z. And then for the B, it's literally just going to be everything that these 3 are equal to. And it's going to be, you know, in accordance with like, so this is going to be in the same kind of order as the, you know, as the equations that we were given. So first equation goes with, you know, row 1, and then row 2, and then row 3, right? And so this is our matrix A, and this is our matrix B. And what we're going to do for Kramer's rule, right, is we're going to just find the determinants of all of these kind of separate matrices. So for the first matrix, it's just going to be the normal matrix A. And what I used to find this determinant is the hollow wicker basket method. And I got -3 from it, right? So I'm not gonna really explain the hollow wicker basket method because that's kind of for a separate video. But yeah, it's not too bad though. A quick rundown of it is that you multiply these diagonals, right? Like the major diagonals. So boom, 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 right? And you add those together, and then subtract it all from the added up of the other diagonals. You know, the minor diagonals, which is 5, 2, and then 18 for this, right? So, you know, major, all of the major added up minus all of the minor added up, and that gave me -3. And then what you want to do for the other matrices, right, is for A1. So since we have 3 variables, we're gonna have 3 different extra matrices, right? And so for the first extra one, we're going to so for A1, right, specifically for A1, we're going to replace the first column right? Because it's called A1 because we're going to replace column 1 with our numbers from matrix B, right? So this is our normal matrix, right? And then we're going to replace column 1 with matrix B, right? Specifically for A1, right? So -2, 5, and 6. And that's all we do for A1. And then we find the determinant of that. And the determinant for this specific matrix, right, for A1 is -3. And then we do the same thing for A2, right? But it's A2. So for A2, we're going to replace column 2 of the original matrix, right? So this is still 1, 2, 1, right? Because we're not replacing column 1. And we're not replacing column 3 either. We're only replacing column 2 because it's A2, right? So we're replacing column 2 of the original with matrix B. So boom, boom. We're just kind of slotting that right in there. And then the determinant of A2 is just 6. And similarly for A3, right, we have our original matrix here. And since it's A3, we're going to replace column 3 of the original matrix with matrix B. So column 1 stays the same, column 2 stays the same, but column 3 of A3 is going to be replaced with matrix B, right? So this original column here for A3, right? So this A3, we're going to replace this third column of A with matrix B. And that's what we do for all of the new A's, right? So for like with the A's with subscripts. With the original determinant of A, you obviously don't need to change anything about the matrix, so you just take the determinant of matrix A, which just so happened to be -3. And specifically, Cramer's rule gives us that the new matrix divided by the old matrix, right? So A1 divided by the normal determinant, right? So determinant of A1 divided by the determinant of A. So A1 was -3, and then the determinant of A was -3. So -3 divided by -3 is 1. And why does this equal x? Well, this equals x because A1 correlates with x. Because it's our first variable in column 1. It's our only variable in column 1 because that's what column 1 kind of defines. And for y, our second column defines y, which is why A2 is defining y. And then similarly for z, right, since z is in that third kind of column there, right, A3, which is fully kind of, which we're replacing column 3 of the original, right, with B, z is defined by A3. And yeah, so x is defined by column 1, y is defined by column 2, or A2, right? And then z is defined by A3, or column 3, right? And then all we're going to do, right, is like I kind of said before, so for x, it's A1 divided by the old A, which is -3 divided by -3, which is 1. And then the y is going to be A2, because in this example, our y is kind of situated in this second column here. So A2 is 6, right? So 6 divided by -3 is -2. And then similarly for z, it's going to be A3, which is -9, divided by -3. So -9 divided by -3 is 3. And these numbers, so these numbers is a coordinate on a xyz plane that is the solution to this systems of equations. And that's what Cramer's rule does. It gives us a solution to a systems of equations through determinants. So yeah, I hope the video was helpful, And yeah, if anybody wants me to give them a shout out, please comment below. Oh yeah, maybe I might need like an intro and outro soon, but it's honestly like not super needed, but be kind of cool, I guess. I don't know. But yeah, hope you guys had a fun time listening to my rant, and maybe might do better on the test because of it. And if you're not listening to this because of a test or anything, I hope you had just a nice, jolly old time listening, and hopefully, perhaps taking something away from this video, or maybe you fell asleep. I'm glad if you did, because that's something else that I contributed to, and I'm glad to be a part of it. So, I hope you guys have a wonderful day, and I will see you all in the next one. Peace.